since when he joined our PhD program, right? So, but it looks like many years have been passed. So he's the one in our team, which is, you know, I like the kind of like a label, like a Superman label, and I can put on him because he can almost take on any tasks or any missions, right? So when we need him, right? So he's one willing to offer help and also provide very strong support to many other team members in my group. So I'm kind of feel fortunate to have him. Has been working with me in the past few years. He also very productive so far. Has been published many papers and also very active. I very actively participated in many events, including our CCDC competition. Has been served as captains of the team for 3 years, right? And also recently he joined the CCDC Black team to support the CCDC, which is a significant contribution from students, right, for this national level of activity. In addition to that, in addition to the research, so I think Ankur is also very capable to handle the real world issues, right? So he's one of member in our group who can do both theory and also the practical hands-on stuff. So that is not very common in my point of view, right? So in many of our computer science PhD students, right? So that is a because I feel he has a great future, right? So if you can explore any directions, right? So he'd like to be. So today, what he want to present is a software-defined situation-aware cloud security. So this research topic we has been studied for many years. I think since the booming of cloud computing back in the 2008, 2009. So we put our efforts into that, and then gradually we move into the software-defined systems, the programmable network, and also we gradually move into the adaptive security, especially the moving target related security problems and issues. Right? So he has a lot of research outcomes in this field. Right? So today, he want to present his work, and let's start. And this just serve as an introduction. And if we have any questions, and feel free to stop him and ask. Ankur, so we would expect there's about 40 minutes presentation. So please control your time, and let's begin.
Yeah, thank you everyone for joining my dissertation defense. And I would like to thank the committee members, Dr. Dijan. He has been great support in all my endeavors, be it academic or be it some cyber defense competition that I participated in. And Dr. Rao, he has been a great collaborator on many of the research works that we have done together. And I would like to thank Adam and Tiffany for their classes that I attended. And I have been fortunate enough to do some work with both of them. Under Adam, I was a TA, and I worked with Tiffany on cyber deception project. So that has been a very good learning opportunity. And I'm glad that I have the kind of committee that have taught me and helped me become a better engineer and a security researcher. So today I'll discuss this topic, software-defined situation-aware cloud security. To begin with, I'd like to highlight the problems that we'll be checking during the course of the discussion. So first thing is, how do we represent multi-stage attacks? We have scalable attack graphs for representing multi-stage attacks. Then we deal with the special category of multi-stage attacks known as advanced persistent threat. And I'll highlight the data set that we produced, the APT 2020. So this was joint work with me and Soumya. And then how do we check if we can employ some proactive moving target defense-based countermeasures. In this area, I contributed Markov Game as a means to deploy proactive security. And finally, when we implement these countermeasures, we need to make sure that they do not disrupt any quality of service or security in the system. So as a contribution, I contributed a parallel hypergraph partitioning based algorithm for attack graphs. It proved to be 3.9 times faster than state-of-the-art algorithm, which was based on malware. And basically, for a special category of APT attacks, I contributed with the dataset DAPT 2020. Then in terms of moving target defense, I analyzed zero-sum Markov games. And in my joint work with Selig, I extended it to the general sum game case as well. And we observed that optimal mixed strategy that we devised based on this Markov game formulation was better than random and min-max pure strategies. And finally, in terms of the conflict analysis, I employed bounded model checking to reduce the scope of conflict checking at the data plane, which induces a lot of security and quality of service issues. So if we look at the abstract model of SDN, we have data plane where we have a lot of forwarding devices, basically switches, routers, which should be OpenFlow capable. And in terms of the control plane, we have a lot of network operating system that act as kind of the brain of this environment. And at the application level, we have users and admins who deploy some applications like access control list or the QoS application for this environment. So basically, the southbound REST APIs are used as a communication mechanism between the control plane and data plane, and the northbound application APIs are used for communication between application and control plane. And through the course of this discussion, we will see that at what particular places there can be some issues which we are trying to address. So if we look at threat model, we consider attacker who is trying to exploit the system. Basically, there are, say, two tenants in the cloud network, and attacker is planning to employ a multi-stage attack. So his idea is that he will target the virtual machine 1 on tenant 1, and then do a lateral movement to target virtual machine 4 on tenant 2. So this multi-stage attack is something that we are planning to model using attack graphs, which are a tool. Basically, attack graph has vertices and edges like any graph. The vertices can be conjunct node, which basically represents the preconditions of the exploit, as I'll explain in the next slide. And the edges basically connect the vertices together using some first order logic rule. And the result of the exploit is basically disjunct node or the post conditions. So basically, some preconditions must be met in order to trigger a rule. And basically, a post condition can lead to further exploits. So one example is suppose the example that we discussed, the virtual machine 1 with the web server. It had a particular vulnerability, and there is network connectivity for attacker to basically target the web server from internet on port 80. And basically, the vulnerability has property that it is a possible remote exploit. So it can trigger interaction rule, basically leading to this post condition, which results from this exploit. So if we put this in form of possible attacks and construct a graph, this is something that we will obtain. Basically, the virtual machine 1 has remote code execution vulnerability, and there is a user privilege on this VM that attacker has. So this interaction rule will allow the attacker to gain a root privilege on this machine. And further, like as we mentioned that the target of attacker is SQL vulnerability, which might contain very sensitive information like payment card industry information or the records of the users. So he can employ another vulnerability on the VM4 to target the SQL server. And if we represent all this information in a graphical format, this is something that we will obtain. So I mentioned in very detail about the attack graph work that we did. So during the course of this current discussion, I would like to focus more on the recent work that I've done since my proposal defense. So we looked at a special category of these attacks known as advanced persistent threats. So the thing is that the traditional security tools, which are based on signatures, they find it very hard to detect these advanced persistent threats. And we need some machine learning models to capture both contextual and collective anomalies to basically identify these APT patterns. So to define APT, basically the attackers employ some advanced tools and threat vectors, and they are not like normal grab and go kind of attacks. So the attackers want to maintain persistence over a long period of time. For example, the Sony hack that happened, the APT was performed over 147 days, and it can lead to loss of data and critical information. So basically an APT attacker pursues his objective over a long period of time, and he's able to adapt to the defender's efforts. So for example, if there is a IDS on the system or antivirus, the APT waits out the scanning cycle of the IDS or antivirus. And basically they, like if there is some break in the connection, the APT attacker will be able to regain the connectivity based on some of the malware that he has deployed. And it is an important problem because as you can see, it has impacted most of the sectors that are mission critical or are important for the safety. So we will take a look at a small example to see how the APT attack happened on the target, which was a big case a few years back. So basically, the attackers first compromised a vendor PC, which was located at the edge of the network. They used the vendor PC to gain access to the vendor application. So they performed reconnaissance and foothold establishment to gain access to the vendor server. From there, they performed a lateral movement to target an internal Active Directory server. From Active Directory server, the attackers went on to this point of sale machine, which had credit card and PII information of a lot of the users. And from there, they used channels like FTP server to exfiltrate the data out of the network. And through this chain of steps, they perform the entire APT attack. So right now, there are some machine learning models that are employed for APT detection. Like one class SVM is a useful model in the cases where there is high class imbalance in the data set. Then stack autoencoder basically is a feed forward neural network, which is used for compression of the input features followed by reconstruction. And we are trying to see how much the reconstructed output is away from the original input. And that helps us in identification of the outliers, or in this case, APT attacks. So another popular model is LSTM, long short-term memory stack autoencoder, which is mainly used for forecasting the time series data. And it is very useful for discovering a pattern of events. For example, we saw that there were a series of events that happened in time sequence. So that's why these have been some of the methods that are used in APT research. So we constructed this APT data set, and we compared it against the existing data sets, and we found that we were able to cover most of the attack vectors, and even some of the attack vectors that were missing in the existing APT data sets. And ORS was the only data set that covered all the phases of the APT attack. Even the lateral movement and data exfiltration were some of the key phases that were missing in the existing data set that we were able to cover. So we established a small network using container framework. And what we did was we brought in a set of penetration testers. They performed the baselining of the environment by doing normal activities on day one. On day two, they performed some reconnaissance activities like using Nmap, Dirbuster, Nikto, Burp Suite. Uh, on day three, basically they established the foothold on the edge machines on our network that we created. And from there on, they tried to compromise the private network that we had, which was a little bit difficult to exploit. But eventually they were able to went on to private network. And on final day, they performed data exfiltration. Basically, we had some SMB servers, Google Drives, and they also employed some tools like PyExfil to exfiltrate this data out of the network. So it was interesting to observe that when we plotted the precision and recall curves for different machine learning models on our data set, as well as the data set that we benchmarked against, uh, that most of these data sets were only able to detect the reconnaissance stage correctly, like as you can see, in this case, the CIC-IDS 2018, the reconnaissance is easy to basically identify. And one of the reasons is that the attack percentage of the reconnaissance is very high in these data sets. So we are arguing that you can do this using a normal signature-based detection mechanism. But in case of APT attacks, like if you see, the percentage of the attack traffic will be very low. So these data sets and basically these machine learning models will not be as good. So when we try to use these models on lateral movement and data exfiltration, like static autoencoder, you will see performed very badly. So we also analyzed long-term short memory, and on the CIC-IDS 2018 and 2017, the reconnaissance stage was detected fairly easily on this machine learning model, but it struggled to detect other stages like foothold establishment. And as we discussed, the lateral movement and data exfiltration was missing in all these data sets. And basically, support vector machine performed the worst of all. Basically, we had a baseline here. Basically, this dashed line represents no skill classifier. Basically, like if there is no pre-training on the classifier, how easily it is able to detect the samples of the positive class of the traffic. So you can see that the SVM is performing as badly as the no skills classifier on the dataset UNB 2015 and even the CIC-IDS 2018. It performed very poorly. So we made some observation that detection of APT attacks using existing machine learning models, as well as the data sets that we benchmarked, it is quite challenging. So we do need some better machine learning models. And this kind of leads into the next section of the discussion, which is that why not employ some proactive means for dealing with these attacks? And that is where we employ moving target defense. So imagine a static system. Basically, you are sitting ducks if the attacker can perform reconnaissance and identify what vulnerabilities are present in your network. But if you have kind of a dynamic system, the idea is that a moving target is very difficult to hit. And we employed SDN-based moving target defense in particular because SDN is in a central location in the network, and it is able to identify any changes in the network easily. In our survey for SDN of moving target defense tools and techniques, we identified that most of the solutions, at least 34% of the deployments were using SDN and NFP. And why do we want to analyze any changes deployed by MTD in the system? That is because in another survey, it was identified that these middle box deployments, the misconfiguration is a very large portion of the failures on these middle boxes. So we want to make sure that we have this situation awareness, like any changes we deploy in the system, we are able to track and make sure that it does not adversely affect the system. So we came up with this Markov game formulation. Basically, this was joint work with our lab and Dr. Rao's lab. So we had a two-player game that we formulate in this case, and it is basically a zero-sum game. S represents the state of the game, and in next slide I'll show like what the implication of these states are. And A represents the actions that can be taken by attacker, A1, and A2 represents the action that can be taken by defender. T is the transition probability. Suppose in state S1, the attacker takes action A1 and the defender takes action A2, with what probability the attacker can transition to state S dash. And R is the reward obtained by each player. So we use temporal difference learning to estimate the optimal value of the reward in this Markov game model. So basically, we have this min-max formulation. Basically, the calculation of stationary policy is the probability distribution over the actions that each player can take. And basically, we are trying to estimate the Q function using this temporal difference learning. And gamma is basically a discount factor. So high value of gamma means that it is more desired to be in current state, and a low value means that we are placing more emphasis on the terminal states. So let's see that for the initial example that we showcased, the attacker has possible action, like he can choose to do no action, or he can choose to exploit the web server, or he can choose to exploit FTP server on this machine. And similarly, the defender can choose to deploy no monitoring, or he can choose to deploy monitoring on either of the services using an IDS system. In one of the works, basically, that we have in GameSec, we showcase that the deployment of these monitoring mechanisms, IDS in particular, has some impact on the performance of the network. So this will basically be a penalty to the defender. So he has to be strategic in deployment of these defense mechanisms. So if we relate it with the attack graph that we initially described it, this will be the Markov game graph. So in state S0, consider the attacker is basically having a user privilege on VM1. And the possible action he can take is either no action, or exploiting web server or FTP server. To each of his action, the defender has a possible action, like he can choose to monitor, or he can choose to not monitor. And based on these extended form of game, the attacker will transition to state S1, or he will remain in state S0. Suppose both of these players take no action, basically he remains in state S0. And this way we formulate the Markov game graph based on the attack graph that we initially proposed. So if we consider the reward modeling on this graph, we used two means to determine the reward. So one is the impact score that is part of the vulnerabilities CVSS score. And the negative values indicate that security is always a negative cost for the defender. And suppose like the attacker takes no action, but still the defender is monitoring his system. it's a negative cost for him, basically the cost of deploying the defense. So this first table is the reward model or the reward cost in the state S0. And second table is the cost he has in state S1. And basically, we have a zero-sum game. So whatever will be the utility to the defender, it will be exactly opposite for the attacker. And we also made sure that we model the transition probabilities. In this case, we use the access complexity as a means for modeling the transition probability. So it makes sense that if a vulnerability is having low access complexity or easier to exploit, it is easier for attacker to transition from one state to another. So we put the values 0.02 for low access complexity, 0.6 for medium, and uh, basically zero point 0.2 for high, and 0.9 for low access complexity. So basically the idea is that if the attacker can exploit a vulnerability with fairly ease, there is a high transition probability that he will go to the next state, basically, which is from user to root state on that machine. So we calculated the optimal countermeasures utility for both, in the case of Defender, based on the optimal mix strategy, the min-max pure strategy, and the uniform random strategy. So min-max pure strategy means that if there is a pure strategy for placing the defense system that clearly dominates the placement of security on all other system, that will yield the highest reward. And uniform random strategy means that with equal probability, we deploy the defense on all these systems. And optimal mix strategy, which is the top line in our case, yielded better utility for Defender as we increase the value of the discount factor. So what this means is the higher values for discount factor, the high magnitude of reward is for the Defender in the terminal state, which basically increases the magnitude of gain correspondingly. So our strategy in this case clearly dominates the uniform random and pure strategy. And for the initial example that we discussed, we found out that for the Defender, it is optimal to do monitoring with 0.26 probability for the web service, with 0.43 probability for the FTP, 0.3 for the FTP service, and no monitoring for with 0.43 probability. So it kind of makes sense that in the states that are farther away from goal state, we can choose to do no monitoring, basically to save some performance cost. But in the state S1, it makes sense to do monitoring with a combination of this 0.5 and 0.5, because it's a very important state in this game formulation. So we also modeled a case of advanced persistent threat. Basically, we simulated a network from the Western region cyber defense competition. And the idea was that the red team had to first compromise a firewall vulnerability and then use it to target the Active Directory Windows machine, and finally target a machine that had important information on the internal network. So when we analyze the strategy, which is uniform random, basically the moving target defense in this case was to place the IDS system against each of these vulnerabilities on the internal network. And we had, as you can see, several possibilities, 5 in this case, for placing the detection system. And when we compared it to the uniform random strategy, the MTD strategy that we proposed clearly dominated the uniform random strategy in case of this simulated APT attack. So in the final part of the work, basically we analyzed like if the network administrator is deploying some of these MTD countermeasures at the application plane, we want to make sure that it is easy to check any security and performance implication that it can have on the system, because in past it has been observed that misconfiguration was one of the reasons that led to the Capital One hack and some of the other security outages. So basically the idea was to create a intent-based framework at application plane, which can reduce the overhead of checking some of these rule conflicts at the data plane in this network. So if we have basically an interaction between the user and the user asks the admin like, what kind of system do you have? And admin replies that we have the system. The user is not that much concerned about what kind of control plane software the admin have, but user is only concerned that some of his requirements basically that he can express in form of natural language, like the traffic should be always allowed between two edge servers, and some of the SSH traffic should be blocked between two machines. He wants these requirements to be satisfied, and these can be satisfied by the admin using some of the security policies. But what if user asks, like, is there a way to make sure that these changes do not impact the performance or safety of my system? Then admin basically is kind of thrown off. There is no clear way to answer this. And that is why we designed the system INTPOL, basically, which checks in an abstract way, like if the changes that will be deployed to this system impacts the security or performance in any way. So if we look at the OpenFlow network, that is basically the data plane of the SDN environment, we have certain security functions like flow switching, basically allows the traffic between two machines, and basically firewall or access control list blocks the traffic between certain regions of the network. And we identified that many of these functions have common set of fields, like they have the header space, which is basically layer 2 to layer 4, the rule that is applied to a certain kind of traffic, and priority of these rules. So we observed that there can be some cases of conflicts. Basically, if we look at the flow rule 1, basically it allows the traffic from source IP1 to the destination range. But flow rule 2 basically has this different action which contradicts with the action of the drop. So these two flow rules can be in conflict with each other. And similarly, there can be some transitive level conflict. So for example, flow rule 1 here asks the traffic to be dropped, but flow rule 2 says that forward this traffic to the source IP5. And flow rule 4 says that any traffic between from 5 and 8 forward it to destination IP2. So if we check the combination of rule 2 and 4, basically violate the requirement that we had for blocking this kind of traffic. So to deal with this, we came up with this intent-driven policy management. So the idea is that there are multiple controllers at the control plane, and we need an abstract language to accept and validate the user requirements. And the framework, basically, we were doing this project with Naval Research Lab, and they have certain part of the network which is non-OpenFlow as well. So framework should seamlessly be able to cater to the non-OpenFlow network as well. So we came up with this grammar, basically, which abstracts the network admin security and mission requirements. And we use the bounded model checking to ensure that we are able to calculate or find any security or mission requirements in linear time. And we also tested this on non-OpenFlow domains and cases like service function chaining as well. So we use linear temporal logic in this case. Basically, it's a mathematical language which uses symbolic model checking to see the reachable states, and it simulates all possible behavior based on the execution of system, and it tries to generate a kind of a contradiction to the requirement, which is known as a counterexample. So it provides a useful way of representing the network properties, and it allows the use of theorem proving to check if the security and mission requirements are satisfied in optimal manner. So two examples here we have is the safety requirement. So suppose we say that two processes cannot be in the critical section at the same time. So we can express this as a LTL rule. So G means globally. So globally, it should not be true that process one and process two are in critical section at the same time. And liveliness says that whenever a process wants to enter the critical section, it should be eventually able to do so. So F here represents finally. So globally, it should be the case that if the state is initially entering, then finally it should be in the critical section. So if we model our network requirements using this LTL formulation, basically we can say that HTTP traffic from these two edge servers and these two hosts, basically this intent should be allowed to pass traffic from host one on edge server one to host one on edge server two. So we say that if there is a packet, then globally it should be the case that if a packet is sent from host one and it is of nature HTTPS, the final result should be that packet is able to reach host one on edge server two. And this is another rule in the reverse direction. In case of SSH, we want to block the traffic between two edge servers. So we say that if there is a packet and it is sent from host one on edge server two, it should never reach the edge server host H3. Basically, we are blocking this traffic and representing these as network invariants in our model checking framework. So this is the overall architecture. Basically, at the application plane, we have two types of intent. One is policy intent, which is constructed based on the reachability from the network controller and the existing policies that are present in this model. And policy intent is basically set of requirement on this framework which check basic reachability if there are policy conflicts in this model. So anytime there is a policy conflict or reachability violation, the model generates a counterexample and sends back to admin to say, hey, what do you want to do about it? Like, do you want to correct it in some way? And if there is no counterexample, that rule is basically inserted in the OpenFlow network using OpenFlow APIs. So this is the grammar that we proposed in the work that we recently submitted to NSDI. Basically, we represents the intent type as policy and query intent. The policy intent can be either a network function or a service function chain. And service function chain is basically a series of network function that we want to add. Basically, some network would want to do firewall followed by load balancing. So that represents a network function. And if we zoom into one of the network function, firewall in this case, we can say that it will have a header and action. And there are layer 2 to layer 4 fields for header, and actions can be in an abstract form forward, drop, or modify. Similarly, the query intent can be to check conflict, check reachability, and we use some of the LTL rules like FP means that the invariant that we described P holds in all future instants, and GP means that it should globally be true always. P union Q means that P holds until a state is reached where another invariant Q holds. And XP means that in next state, the invariant should be true. So we constructed a linear temporal logic based model. We encoded our security and management policies and basically used the query intent to express any properties like tenant isolation, packet reachability, checking forwarding loops. Because LTL in itself is P-space complexity, we used bounded model checking. Basically, what we did was placed a bound on the model based on the uh, means, which is recurrence diameter. Basically, we checked the longest path in the network and use that a means to place bound on the model that we had. And for a given transition system with S states, the model had complexity k into S. And basically, this reduced or bounded model of LTL then uses the SAT solvers to handle the propositional satisfiability. One disadvantage of this is that if there are highly complex cases, then this bound may not be able to cover that. But we found that in the case of the networks that we were dealing with, the bound that we established was sufficient to do the coverage that we wanted. And another reason for using a bounded model checking is that it's also quite common in planning domains like AI search. They place uh, bounds on the search to make sure that it is satisfiable within certain range. So if we look at the service function chaining, how we can model it using LTL, basically there are few service function chains that we have here. The first one says that any traffic from endpoint group 1 should reach endpoint group 2. So it should pass through a series of service function like NAT, firewall, and the packet inspection. And similarly, we have some other service function chain requirements. So we can express them as LTL model. Basically, variables represent basically the destinations and intermediate steps. And the next function says that suppose it is currently the NAT where the packet is located, and the destination is endpoint group 2, then the next place where packet should go is firewall 1. And it is a very simple example of the model that we created. And we can specify the initial network function or service function as NAT in this case. So if we zoom into a particular network function, firewall in this case, basically we can represent some of the firewall requirements using this bounded model. So we consider the source and destination to be the host that are part of this firewall, and it can be extended distributed firewall as well. And we say the next states are switches in this case. So we say that if the current switch is S1 and basically destination is not host H1 and host H2, the next place where the packet should go is basically switch S2. And if we have certain requirement like traffic sent by host H1 should eventually reach this host H5, we can express these in form of the queries or the query intent that we discussed on this model. So we say that the bound on this model is 5, which is basically the width of the network in this case. So we say that tell us if the bounded model can find a countermeasure for this rule, where we say the source is host H1 and it is reaching host H5. So if there are any loops in the network which are basically violating this invariant, those will be sent back to user as counter example, and he can correct that. And similarly, if there is another kind of traffic which is blocking intent, we can say that tell us the cases where this intent is not satisfied within a bound 5, like if source is H2 and the destination should not be globally H4. So because we were also planning to deal with some hybrid networks, if you can see in this network, the backbone is the OpenFlow network, these switches that represent, but the core network is non-OpenFlow. It is managed by BGP routes. Basically, there are autonomous systems, like the router one is managing host H1 to host H10, and we say this autonomous system 6501. And we have, say, 10 routers, and this router R10 manages the host from range H91 to H100. So we can represent this hybrid network using the modeling in linear temporal logic. So we can consider that at an abstract level, there are switching functions and there is a NAT function. And we can represent them in form of the service function chain, like any traffic from autonomous system 6500, which is this network, should go to a NAT and then go through switching. So we tested this hybrid network scenario, and we observed that as we increased the number of domains or autonomous system, the bounded model that we used in case of INTPOL framework, it was 2 times faster than if we do a full-scale model checking. So for, as you can see, for 10 domains, the time required for LTL is 0.016 seconds, and for bounded model is 0.07. And within a domain, as we try to increase the number of hosts, the bounded model was still faster than the full-scale model checking in terms of the time required for computation. So we increased the number of hosts from 5 until 40, and also the number of nodes that are generated by this bounded model. And finally, we tested it on extended network. Basically, this is the Stanford network that is used in the policy conflict research. It had 757 for 1,000 forwarding rules and a lot of routers and switches. And we observed that, like, as we increased the number of requirements from the application plane or the intents from 20 to 100, there were a lot of flow rules that were generated in this network. And the scope of flow rule conflict checking, basically, if we don't use the INTPOL framework, is kind of a quadratic increase in time. And if we handle some of these conflicts at application plane, as you can see that the time required is linear in terms of the number of rules and intents. So some key observations were that we can represent these different network function and service function chaining requirement using our framework. And bounded model checking reduces the scope of security and mission violation in our framework. So in conclusion, I proposed a scalable attack representation framework, then analyzed a special case of APT attacks, and contributed a data set for APT detection and benchmarking the machine learning models. Then I proposed a Markov Game model for strategic detection of threats and doing the MTD to deal with these threat activities. And finally, I analyzed the conflicts that can happen because of the MTD countermeasures or the general policies that are implemented in the cloud network. So this is the research publications that I have done since my proposal defense. Basically, some of these works were not in line with the dissertation, so they could not be included in the presentation, obviously. And basically, we have some research in review already, and basically my work has been cited nearly 331 times, so forth. So the highlighted ones are the papers where I am first author. So apart from that, I have been quite active in commercialization of the SDN research. Basically, we co-founded Cynet LLC, me and Dr. Huang, and it won some startup competitions here at ASU. And I have also presented at several industrial conferences like DEF CON and CactusCon. And another significant accomplishment was to co-author the textbook on SDN with Dr. Huang. As a contribution to the academic domain of the school, I co-founded DevilSec Hacking Club here at ASU, and we have over 250 active members, and it's a good way that we can help students build their career in cybersecurity. And as Dr. Huang mentioned initially, I was also captain for WRCCDC. And I have mentored several capstone projects, like one I mentored with Tiffany. And I was also awarded Outstanding TA when I was TA for Adam during 2016. So in conclusion, I would like to thank all my friends, all my team members who have been part of research, Salik, Hakeem, Adel, Soumya, all the other members, Neha, Garima from our lab, everyone, and my team members at DevilSec, Alan, Matt, Gabe, Joe, and Sarah, and everyone else at DevilSec who helped me teach cybersecurity and helped me learn a lot playing with them on various cyber defense competitions. So with that, I'm open to any questions.
All right, very well. So thank you for the presentation. So now it's time for questions from the audience, from committee members. If you have questions, please.
Okay, I would like to start. I have a question, yes. Ankur. First of all, this is a fantastic defense. This is a good presentation. I really enjoy it. And then I really like that you contain a lot of information. And it's really good for me to know that, you know, our current adaptive cyber defense is getting more and more scalable. So yes. I have a high level idea. I have a high level question. So can I know, yes. like currently, what is the biggest bottleneck, like stopping it from more scalable?
Yeah, so biggest bottleneck is like different kind of deployment frameworks that we are planning to deploy the system on. Like suppose you want to deploy it on OpenStack Cloud, that is very different from deploying it on AWS system. Like when we tried to present this MTD for commercial work, one big bottleneck was that people were not as receptive as like as you would expect them say like, hey, I don't have any control. You just want to take over my network, do a bunch of changes. It can impact my user. So I would say the fear that it will impact the users or the normal functioning of network in some unknown way, and the different kind of backend frameworks where we have to deploy this solution. Those are the two big bottlenecks for adoption of this work.
I see. Yeah, this is good explanation. Thank you.
Yeah.
I can go next.
Yes.
Great job, Ankur. I really enjoyed the talk. I'm just curious why, for the last project that you presented, why you went with LTL instead of other types of temporal logics like CTL or anything like that. I'm just curious if there was a specific technical reason that had you choose one over some of the other languages and logics.
The one reason was that I wanted to kind of compare it with some of the existing work that were published in conferences like NSDI. So they were trying to use LTL, and I think like CTL can also be used in this case. So for me, the main reason was that some of the previous literature was also using LTL, and I wanted to see like how when I benchmark it on the same data set, how it compares with their performance.
Great. Yeah, that makes sense. Awesome. Thank you.
All right. So then more questions? Yeah, because Dr. Rao, he cannot be presenting in this defense, and he will send me his own questions after this defense, because he has all the presentation materials, dissertation, and so other than the committee members, and do we have other questions from the audience?
Is there something in chat? Let me see quickly. Yeah, no.
Okay, well, so if there's no more questions, I think we're going to go for the private session. Right, so Ankur and the committee member, please remain stay in the Zoom channel, and other audience are excused. And again, thank you for your attending Ankur's defense.
Thanks a lot, everyone. Yeah, so I'm in the lab area, and I've made sure that there is no one in and around me. Yep.
Okay, that's good. All right, so
should
now
we be recording this part or no?
Oh yeah, sorry. Let me stop the recording. Thanks for letting us know.
Yeah, I just never remember, so it's always good to double check, right?